Math 110, Polynomial Functions and Models, Sections 4.1. This is the definition of a polynomial, and it's the generic form. Basically, every single polynomial is a piece of this, per se. It's every single possible combination of polynomials that could possibly exist. That's basically what this definition is saying. Now, the important features of this, your a sub n, this is your leading coefficient, and it corresponds to whatever degree n. N is the degree referring to the highest power. A sub n is the leading coefficient to that degree. Now here's some examples of naming these polynomials. So this would be considered a constant because it's 3x to the 0 power. It's a 0 degree. The leading coefficient is just 3. If I wanted to look at this quadratic, 4x squared, the highest power is a 2. The leading coefficient is going to be a 4. On this quartic, the highest power is a 4. So that's the degree, right? The 4th degree polynomial. The leading coefficient is -1. So these are just some elements to look at, because when we're piecing these polynomials together, graphing, sketching, end behavior, etc., these are the elements that we need to be looking for. Now, some polynomials, they have characteristics in common. First, the domain of a polynomial function is the set of all real numbers from -infinity to +infinity. And all polynomials are continuous on that interval. Now, the end behavior of a polynomial, all we're looking at is what the graph is doing as x is going to +infinity and x is going to -infinity. So you examine it, you look at it, and you're just like, okay, so as x goes to +infinity, and you're basically saying, is my y going up to +infinity, so go to -infinity. You examine those things. Now, the cool thing about polynomials is there's actually certain patterns that arise when it comes to these end behaviors. So looking at those patterns, first we see a pattern when our n is even and odd. Okay, that's the degree. Remember, that's the highest power of my polynomial. And then the second part of that pattern is if your leading coefficient is positive or negative. If my degree is even and positive, my graph, the ends of it, so my end behavior, they're both going to go up to +infinity, right? My y is going to go up to +infinity. If my leading coefficient is negative, they both go down. When it's odd, it's going to go up in this direction and down in that direction, and then when it's negative, it flips, because negative means a reflection over the x-axis. So for this first example, it says sketch the end behavior of the following. So what I need to look at, it says even, what I need to look at is the degree and the leading coefficient. So my degree is 4, my leading coefficient is 3. So looking back at this, 4 is even, that 3 was positive, so my end behavior is going to be that shape. So the sketch I would do would be something like this. I just know because of that pattern that because my degree was even, they're both going to go up, and because my leading coefficient was positive, they're both going to have that same shape. They're both going to go up. Now looking at this, we have negative and odd. So going back, negative and odd is going to be this one here. So my graph is going to have this shape. Now I'm just doing a brief sketch. I'm just briefly sketching it. It's not anything exact. This is positive and odd. So therefore, looking at the chart, positive and odd, it's going to have that shape. And then this is negative and even. And so looking at that graph, it's going to have that shape. Now you need to memorize these end behaviors. We need to know them because when we're sketching polynomials, it's going to help you with that. But B, also kind of getting an idea of what the polynomial is doing is definitely going to help you analyze graphs in the future in math. Now just a quick reminder when it comes to zeros. Okay, the zeros of a polynomial is where the graph crosses the x-axis. So to verify if a value is a 0, whatever value it is that you plug in, okay, if you end up getting 0, then you know that it's going to be a 0 of the polynomial. So if I plug in 2, and I get 2 to the third power plus 2 squared minus 17 times 2 plus 15, the question is, does that equal 0? You would get 8 plus 4 minus 34 plus 15. 12 minus 34 is negative 22 plus 15. That's not going to equal 0. Now if you plugged in negative 5, you would find that negative 5 does equal 0. So negative 5 would be my 0, 2 wouldn't be a 0 of my polynomial. Now visually, these are what zeros are going to look like. If we take a look at this graph here, as we notice, if I were to graph this polynomial here, it's going to cross the x-axis here at -1 and +2. Now how did I find those zeros? Remember, we're going to use the zero product principle. And so because I set this thing, entire statement, equal to 0, then I can set each of these factors to equal 0. So this would be x minus 2 equals 0, x minus 2 equals 0, x minus 2 equals 0, and x plus 1 equals 0. Now solving for those, you're going to get x equals 2 and x equals -1. So these would be my zeros of this polynomial. Now one thing that we're going to kind of pay attention to is notice that, yeah, I didn't write the repeats, even though technically there was quote-unquote 3 positive 2's as my 0. That does mean something, and we're going to come back to that very shortly. On our next example, once again, I would have to say x minus 1 equals 0, x minus 1 equals 0, x plus 2 equals 0, x plus 2 equals 0, and solving for these, you're going to get x equals 1 and -2. Notice, take a look at the graph, kind of hits that point at -2 and hits it again at +1. So this is where having those repeats are going to come into play. And this is where we're going to go to multiplicity. Basically, multiplicity tells us how the graph interacts with the zeros. So if we know that this is a simplified form of that multiplicity, if we know that x minus c to the k power is greater than 1 and is a factor of the polynomial, and we know that the next one is not a factor, meaning we didn't expand it more, if k is odd, then the graph crosses the x-axis at the 0. If k is even, then the graph is tangent, or it bounces at that 0. So k is referring to the number of times that 0 occurs. So if it occurs an odd number of times, we know that it's going to cross the x-axis. If it occurs an even number of times, then we know it's going to bounce at that 0. So let's look at those previous two examples once again. Going back to this example here, we found that our 0 was 2. But if you notice, that 2 occurred 3 times. So because it occurred 3 times, I'm going to say that it's multiplicity 3. My other 0 was -1. It only occurred once, and so I'm going to say that that is multiplicity 1. Notice we said by that definition, when our multiplicity is odd, it's going to cross through that 0. That's what happened here. At -1, it crosses through. At +2, it crosses through. On this next problem here, we said that my zeros were +1, and I have 2 of them. So I'm going to say multiplicity 2. And my other one's -2, and I also had 2 zeros. And so I'm going to say it's multiplicity 2. And so looking at both -2 and +1, if you notice, look at the graph bounces there. Okay, it does not cross through, and that's what our multiplicity said in the definition, is that if it was even, it's only going to bounce at that 0. Now what happens if our graph isn't factored? We're going to still have to try and find those zeros, and right now the only way that we know how to find zeros is basically through factoring. Yeah, we could probably use the quadratic formula, but it's a little bit more messy, and so for most of these we're going to be practicing factoring to be able to find those zeros. And so to be able to factor this is factored by grouping. So we do that little dividing line down the middle, factor out what's in common, and so that's an x squared, and I'm going to be left with x minus 2. I can factor out a negative 9, and I'm going to be left with x minus 2. And so grouping these together, I'm going to get x minus 2 times x squared minus 9. This factors further. This will factor into x plus 3 and x minus 3. So now, stating my zeros are going to be positive 2, multiplicity 1, negative 3, multiplicity 1, and positive 3, multiplicity 1. Remember, we had to set each of these equal to 0 and you solve for it, and when we did that, that's how I got the positive 2, the negative 3, and the positive 3. And so, because I only had one of each, that's why I said multiplicity 1. On this example here, this is going to be u substitution, so I can say u equals x squared. Now substituting that in, I'm going to get u squared plus 4 times u minus 45. This will factor into u plus 9, u minus 5. And so now, substituting the values back in there, I'm going to get x squared plus 9 and x squared minus 5. And so solving for this one, that's not really going to be able to solve because I'm going to get i's. X squared plus 9 equals 0, minus 9 on both sides, x squared equals negative 9 square root. We have a negative inside of a square root, which is going to give us imaginary numbers. Those aren't going to be zeros that we can use. But now on this one, I can say x squared minus 5 equals 0, add the 5 on both sides, so I get x squared equals 5, square root both sides, and you're going to get x equals plus or minus the square root of 5. So my zeros are going to be the positive square root of 5, multiplicity 1, negative square root of 5, multiplicity 1. And that's going to be my answer.